Good afternoon to everyone. My name is Patan Akbar Kalandar Khan. I am currently studying BTech second year in the stream of CSC. My topic is about 0 by 1 knapsack problem. Introduction to the 0 by 1 knapsack problem. The knapsack problem is a classic optimization problem in computer science and mathematics. It describes a situation where you have a set of items, each with a weight and a value, and a knapsack that can be only a limited capacity. The goal is to determine the combination of items to include in the knapsack so that the total value is maximized without exceeding the weight capacity. There are two main types of knapsack problem. 0 by 1 knapsack problem. Each item can either be included or excluded. You can't take fraction of an item. Fraction knapsack problem. Item can be divided, meaning you can take fractional of them. The knapsack problem is widely used in areas like resource allocation, budgeting, logistics, and cryptography, and it is a key example of dynamic programming and greedy algorithm in computer science. Problem statement. The knapsack problem involves selecting a set of items, each having a specific weight and value, to include in a knapsack that have a limited capacity. The objective is to determine the most valuable combination of items such that the total weight does not exceed the capacity of the knapsack. The problem aims to maximize the total value while staying within the weight constraint, making it a classic optimization and decision-making problem. It has various practical applications in resource allocation, budgeting, and logistics. The problem is NP-complete, meaning that no known efficient algorithm can solve large instance optimally in polynomial time. Therefore, different approaches like dynamic programming and greedy algorithm are often used to find exact or approximate solution. Example scenario. Suppose you have a backpack with a weight limit of 50 units. You have items like a laptop, books, and clothes, each with specific weight and values. The challenge is to choose items that maximize value while respecting the weight constraint. This requires finding the best combination of items that offer the highest total value. You cannot exceed the backpack's capacity, so every choice impacts the final result. This is a real-world example of knapsack problem, commonly solved using optimization technique like dynamic programming. Mathematical formulation. Let n be the number of items with each item I having weight wi and value vi. Define binary decision variables xi where xi equal to 1 if item is selected and 0 otherwise. The objective is to maximize sigma in equal to 1 vi xi subject to sigma in equal to 1 wixi less than or equal to w, where w is the knapsack capacity. This ensures that the total weight of the selected item does not exceed the allowed limit. Each decision variable represents a choice to include or exclude an item, making the problem combination in nature. Solving this problem helps determine the optimal selection of items that yield the highest total value. Dynamic programming approach. Dynamic programming solves the problem efficiently for smaller to medium-sized instances. It builds a table where each entry represents the maximized value achievable with a subset of items and a specific weight limit. The algorithm iteratively decides where to include or exclude each item to find the optimal solution. Procedure for dynamic programming solution. Initialize a table dp with dimensions n plus 1 into w plus 1 filled with zeros for each item and weight capacity. Updates the table based on whether including the item yields a higher value. If including the current item does not exceed the capacity, compare the value of including it versus excluding it. The optimal solution value is found of dp n w after filling the table. The approach ensures that all sub-problems are solved systematically, capturing the best value for every possible weight limits. Greedy, heuristic, and limitations. Greedy, heuristic, and limitations. A greedy approach selects items based on the highest value to weight ratio, but it may not always produce the optimal solution. The greedy method is fast but lacks guarantees for the best possible outcome in the 0 by 1 case. Exact solutions often require more complex algorithms like dynamic programming or branch and bound. Applications of the 0 by 1 knapsack problem. The problem models resource allocation tasks in fields like logistics, finance, and project selection. It helps in optimizing investment portfolio by choosing a subset of assets to maximize returns with a budget. In computer security, it can be used to select features or components under resource constraints. Challenges and future directions. Large instances of the problem are computationally demanding, prompting research into approximate algorithms. Metaheuristics like genetic algorithm and simulated annealing are used for rare optimal solutions. Ongoing research explore hybrid methods, combining different techniques for more efficient problem solving. Thank you.